Good evening, everyone. I can't begin to tell you how excited we are to host Dr. Mather in this wonderful installment of the Peyton Rhodes Lecture Series. Truly, our guest tonight exemplifies the qualities that we hope to instill in each and every student here at Rhodes, and I, for one, am thrilled to hear from him. John Mather grew up in rural northern New Jersey, and as a child was fascinated by optics, electronics, and telescopes. He received his bachelor's degree from Swarthmore College and his PhD in physics from the University of California at Berkeley in 1974. He next led the effort to propose the Cosmic Background Explorer satellite, better known as COBE, and then served as its project scientist. The COBE measurements started the era of precision cosmology, confirming the Big Bang theory. This remarkable work earned him and his collaborator, George Smoot, the Nobel Prize in Physics in 2006. Dr. Mather is currently a senior astrophysicist at NASA's Goddard Space Flight Center. He serves as a senior project scientist for the James Webb Space Telescope. This telescope will extend the discoveries of the great Hubble Space Telescope, reaching farther back in time, further out into space, to show us how the expanding universe led to galaxies, stars, planets, and the possibility for life on our tiny Earth. In addition to his Nobel Prize, Dr. Mather has received a number of prestigious awards, including the NASA Distinguished Service Medal in 2007. He is a member of many professional and honor societies, including the National Academy of Sciences, the American Academy of Arts and Sciences, and Phi Beta Kappa. Finally, Dr. Mather is a strong advocate for scientists' involvement in public policy. He even sponsors an internship through the Society of Physics Students that places young physicists on Capitol Hill, where they are able to engage directly with science policy. It was through this internship that I was fortunate enough to meet Dr. Mather last summer, and I couldn't ask for a better sponsor. Don't let the amazing accomplishments I've just reeled off intimidate you. Dr. Mather is one of the kindest and most genuinely caring people I know. That being said, I know you came out tonight to listen to a Nobel laureate and not a college student, so I think I'll wrap it up there, even though I could go on for another few hours at least about all of Dr. Mather's accomplishments. So please join me in extending a very warm welcome to Dr. John Mather.
Well, thank you both for those lovely introductions. And before I tell you many more stories, I want to say when they give a prize for something like what we did, it reflects the work of hundreds or thousands of people. So the particular satellite team that earned a Nobel Prize had 1,500 people in it. And so we never do these things alone. This is not the lone scientist in a lab coat torturing little baby rats. This is people engaged in a huge team. So what I have to tell you, of course, is the work of hundreds of thousands of scientists for hundreds of years, so none of this is new or personal. So maybe I just should say a couple of personal words that I'm just thrilled to be here. And by the time I got here, I knew 3 people already, and I thought, well, it is obviously time I've got to come visit. So this is a great place to, I've really been enjoying talking with the students and the faculty, and so now my job is to make your brain hurt and your heart warm. So let me start with what we have on the screen. Let's put the actual slideshow on the screen, if we could do that in the back there. And I'm going to want to turn down the lights a bit on the screen because I have some beautiful dark-ish pictures to show later. But anyway, I have here on the screen, oh, and I guess I don't have a laser pointer. I'm going to wave my arms. So in the middle, we have a giant golden hexagon. The giant golden hexagon is the mirror of the new telescope that we're building. It's called the James Webb Space Telescope. And that mirror is 6.5 meters. I should use metric units. We should always use metric units. It's 21 feet across, so that's really big. And that's much bigger than the Hubble Space Telescope mirror. It's very powerful. It's bigger than the rocket. I will show you how we fold it up and get it unfolded in space. And this, too, is a gigantic engineering international project team. NASA, along with European and Canadian space agencies, are building this telescope. I'm the senior project scientist, but I am one of thousands of people currently working on the mission. So eventually we will have it into space. Every astronomer in the world will say, I want to use it. We're expecting proposals very shortly from most of those astronomers. So anyway, there it is, and I'll show you later how it works. But before that, I want to show you some of the problems that have been on my mind ever since I was a little guy. So some of them we have learned about more recently. Some of them are still great puzzles. Actually, I think they're all great puzzles on this page. How did we get here? Well, about 1925, almost a century ago, people figured out that particles, we all sort of thought we believed in atoms by then, but even that was pretty new information in 1925. So now we know that atoms are made of particles, and the particles themselves behave like waves. So that's a big mystery. And it even turns out you have to use complex numbers to describe them. That's even bigger mystery. But it seems to be completely true. So now we have these equations, and if you really believed them and were really good at math, maybe you'd be able to predict everything in the world. But we're not. So if you want to know what is concrete like, you have to get some and measure it. So anyway, there is the big mystery number one, quantum mechanics. Where does it come from? I'm not going to tell you because I don't know. We know now that the universe is expanding. I'll show you more about how we figured that out. And it was very smooth and very hot when it was young. And so this is a sort of fundamental story that was a huge surprise when that one turned up back in 1929. We know it has been unstable. People like to think of the balance of nature and isn't everything going to go along more or less the same tomorrow as it is today? So why worry? And now we sort of know that everything is unstable, and we are here because of that. If we hadn't already had a huge number of catastrophes in our history, we wouldn't be here at all. So, of course, the most familiar one is the Earth got whacked by a giant rock from the sky, and it wiped out the dinosaurs, and that was a big catastrophe for them. We kind of like it because we survived. So anyway, it's very unstable, and it spontaneously reorganizes itself all the time. The universe is very large and probably infinite, although I can't prove it to you. Infinite means there's no edge. You cannot come to the last one, no matter how far you imagine going. So there's no limit. That's what infinite means. And so it's old, and it's had time for even what seems to be very unlikely events like us to occur. So when I was a kid, people knew that life was such an unlikely event that it required divine intervention for us to be here. Now, people don't quite think that so often anymore, but we still don't know how it really happened. So now the hunt is on for how did it happen and where did it happen, and are we really alone? So in the last few lines I talk about the possibility of stored information. So now we have information in the computers, and we say, oh, that's information. We also figured out that our human bodies are controlled by information that's locked up in the DNA in our cells. So when I was a little kid, I was 6, my dad told me at bedtime once that we're made out of cells, and the cells have DNA and chromosomes in them that control us. And of course, when you're 6, you have no idea how that worked. In fact, nobody had any idea how that worked in 1954 or whatever that was. So, in fact, I guess it was that year or just about when the double helix structure of the DNA was discovered. And now at least we found out how the molecule was coiled up. But the big question about that is not only the information, but how does the secret decoder ring work? How does the information get turned into commands that control the cells in your body so you can think? How can you think about cosmology if that's not all working? So this is a great mystery. It'll be a big mystery for a long time because it's really complicated. So that has enabled us to be here. It has enabled evolution to happen over generations and millions of years. It's enabled us to figure out that whales, which I got to visit last week, are actually descended from creatures like hippopotamus. And they're closely related hippos and elephants. Who would have known? So anyway, we're here because of that. And the last rather tricky question is, all of our cells are being regulated by control loops. So engineers talk about engineering control loops and feedback. And so am I going in the right place? If I'm not going in the right place, I better turn my steering wheel. So that's a basic example of these things. So this is all going inside your body all the time, and you never notice. But it's what gives us continuity. So I am here, and all my atoms have been replaced almost, except for my teeth and the chromosomes in my nerve cells. Everything else has been replaced over time. I'm still me. Isn't that a little bit mysterious? So that's because of these things that we call control loops, and the biologists here are trying to figure out how they work. The engineers have to figure out how to make ones that work like that so we can have self-driving cars. So we're working on it, but anyway, this is just an example of the hard problems that we are all up against, and we're not there yet. And I think in a few centuries we still won't be there yet, because this is really hard. So here is how we look back in time. So we look at things that are far away. So do you want to know the history of the universe? You see things as they were when they were far away. So build yourself a telescope and look far away, and you'll be looking back in time. So you see the nearest other star besides the sun as it was about 4 years ago. If you could look down to the middle of our own galaxy, see about 25,000 years back in time. If you could look back to what we call the Big Bang, it's almost 15 billion years. So how are you going to know how far you're looking? Well, you survey the universe. You do your geometry, and you know the speed of light. So if you know the speed of light and how far you're looking, you know how far back in time you are looking. So we learned this in school. We're supposed to, anyway. And the top left pictures, and the top pictures, they illustrate that if you know two angles of a triangle and one side of a triangle, you know the whole shape of the triangle. So this is surveying, and we learned it in school, sort of. So astronomers have been doing this. This is the classic method, and it works pretty darn well, as long as you can measure the angles. When that doesn't work anymore, you say, well, I've got one other trick. Let me say, if I can prove to you that those two candles in the picture are really the same, but one of them is fainter, we say it's because it's farther away. So now we can measure relative distances of everything. So that's what we do. And then we say, well, how about things that move? Well, a few things move around the sky fast enough to notice. If you watch the moon over the course of the evening, you can actually see it move relative to the stars. The rest of the things hardly move at all, and it's hard to tell. But there's one trick we have up our sleeve here, which is nature has special colors. If you spread out the light of the sun or chemicals into a rainbow, you can see different patterns. So if you do it really well with the sun, you see the rainbow has dark marks across it, and they're called spectrum lines, because that's what they look like in the instrument. If you look at the fireworks on July the 4th, each of those different colors that you see, the purple and the red, those are from different special chemical elements. So now we can analyze the chemistry of the world, of the universe, by spreading out the light into the colors. So that's pretty cool. Then we said, well, what happens if something's coming toward us or going away from us? And you can tell because all the colors are changed, all the wavelengths are changed in a pattern if something's coming toward you or going away from you. So you can hear it yourself with sound waves. If some madman is on a motorcycle and goes zooming past you on the highway, you'll hear the pitch of the engine drop as they go past. And that's the sound wave equivalent of what we see with light waves. So if we see a star out there that has a spectrum with the colors just the same as the sun, but it's fainter, we say it's farther away. It's the same temperature, it got the same chemistry. So we also say, well, sometimes it's running away. It's going faster away. We can measure that speed. So now we can measure not only the chemistry and the temperature of things, but the motion toward us or away from us. So back in the early 1900s, this was begun. And here is Mr. Edwin Hubble. Let's see, push a button again. Edwin Hubble. Oops, this one didn't work, sorry. That'll have to do. Okay, this is Edwin Hubble, his picture that he gave us in 1929. So with the little dots on here are galaxies. Each galaxy is like 100 billion stars orbiting around a common center, held together by gravity. And each of these dots is a point showing how far away he thought it was and how fast it's moving, and the up is going away. So this picture clearly shows a trend. The farther away, the faster. Divide the distance by the speed, you can tell how long did it take for that to happen. So in 1929, we found out the universe has an age, and he got 2 billion years, which was wrong. Not unusual in science. We get it wrong the first time. Second time, we finally found out what the mistake was. He was using the standard candle method, distances, and the candles he thought were identical were not. So the farther away one is actually 50 times brighter than he thought, and so it's 7 times farther away than he thought. So that explains it, mostly. So anyway, 1929, we were forced into the idea that the universe is expanding. The farther away things are going away from us. Also notice there are 4 of them there in the lower left corner that are coming toward us. It's interesting. Something's going to happen. So the expanding universe, 1929. Einstein had said this could not happen. He gave us the equations that describe it, but then he said, that wouldn't happen. So, and that was 1915 or so, he gave us the equations. 1922, a Russian physicist said, I can calculate with your equations, but I get a different answer. I think the universe is expanding. 1925, he died because he was living in Leningrad, and it was a really tough time to be in Leningrad. 1927, a Belgian priest named Georges Lemaitre, he had his MIT PhD, mathematics, and he said, you know, I can calculate also. I get the same equation the other guy got. The universe must be expanding. Einstein said, no, that can't be. Your mathematics is correct. Your physics is abominable. He wasn't always polite. So anyway, 1929, only 2 years after that, we get the measurement and the graph, and a lot of people are convinced this must be right. Einstein's still not convinced, because how would he have made a mistake? So it took a while longer before the theorists could explain to him why he was really wrong, and he had to believe the measurements as well. So 1929, this is not because theorists thought we should have a Big Bang. We were forced into it by observations. Except for those two guys, everybody was surprised. So what should happen then? Well, the universe must have been filled with heat. If it's expanding, was it hot in the beginning? Well, maybe it was. So in 1965, it was discovered that the universe is actually still filled with the primordial heat. And it's cooler now than it was then. But they measured it, and they discovered it, and they said, well, this is probably it. Took us a while to conclude that, yes, it's probably cosmic. So then I was a graduate student at Berkeley in 1970 looking for a thesis, and the idea was, let's go measure it. So that turned into this project. So my thesis project actually failed, but I got a postdoc position with NASA, and thought I'd try something else. And then NASA said, we want proposals for new satellite missions. I said, we should try my thesis project in outer space. So we called up our friends, we wrote a proposal, we sent it in, we thought it wouldn't win, but it did. So we got to build it. So 15 years later, after we had our sketch, this beautiful bird went into space. So because real engineers worked on it, it actually functioned properly, and immediately gave us the answers that we were hoping for. So number one, the color of the heat radiation is exactly as it should be from the Big Bang story. Number two, that primordial heat radiation has hot and cold spots, and I don't have in this presentation, I don't have the picture, but the hot and cold spots, well, Stephen Hawking saw that picture and he said that's the most important scientific discovery of the century, if not of all time. So I didn't know why he thought it was so cool for a while, but now I can tell you 3 reasons why that was really important. Number one, gravity acting on those spots is responsible for us being here. So thank you, spots. Number two, most of those spots come from something nobody else can see, but astronomers can tell is there. It's called dark matter. And number three, if we ever figure out what makes those spots, maybe we understand quantum gravity. And we don't have a clue yet, or maybe I should say we have too many clues. We have many stories and no much way to tell which ones are correct. So here's our beautiful bird. It went into space, and I'm going to summarize basically all of science about the Big Bang in this one chart. I don't, by the way, cannot and should not draw you a picture. If somebody draws you a picture of an exploding something, they are completely wrong, because you cannot stand outside the universe looking at it to draw you a picture. So what we actually see is distant stuff is all rushing away from us, then the farther the faster. And so it looks to us like we're in the middle. Okay, but are we special? Probably not. So calculate what the people on the next galaxy over would say. They'd think they were in the middle too. So we're all in the middle. So there's no middle. So if you want to know where's the center of the universe, it's that way, it's that way, it's somewhere out there, but probably not here. So even though everything looks like it's rushing away from us, it also looks to every other observer on every other galaxy like it's rushing away from them too. So no center, no edge, probably infinite, although I can't prove it to you, and expanding into itself. All this means is the material is rushing apart. So not even a first moment. So people have been misleading us by talking about the moment of creation. But as far as astronomers can tell, there is no such thing. We always have, in our science, we have ways that something turns into something else. We don't have any way where nothing turns into something. So we cannot say that we've seen the moment of creation. And you cannot even imagine back to before time. So imagine running the movie backwards, say, okay, the universe runs together, hotter and hotter, denser and denser. You cannot get past that. Your imagination just runs out. You say, when I no longer can imagine what was there before, we'll call that the Big Bang. So it is not a big firecracker. It does not have a place. And anyway, probably no end either. Can't prove that. So that's my attempt to make your brain hurt but your heart feel good. So now, what are we going to do? Well, let's talk about how do astronomers decide they want another telescope? So this is a sort of story because I think it might be interesting to you how astronomers do our social thing. We are not alone. We have parties, and we call them committee meetings. And so every now and then we say we got to have a committee to talk about what do we do next. So in 1989, even before we launched the Hubble Space Telescope, astronomers had a conference to say, well, this is what we're going to do next. And some of them said we need to build the thing that we actually ended up building. And more meetings were held. In 1990, there was a committee that said, what are we going to do next? This is a nationwide committee. And they said, yeah, we're going to need a big telescope in space. But they didn't make it their top priority. So then Hubble flew in 1990, and it's almost 28 years old. Next month it'll be 28. Can you imagine that beautiful bird being 28 years old? And it's still working beautifully. Of course, there's a reason for that. We went up with astronauts 5 times to make sure. First we had to fix it because we made a mistake, and then we had to upgrade it 4 more times after that. So pretty fantastic approach to doing space astronomy. We couldn't know almost anything that we know about astronomy today without that telescope. If you open up your astronomy book, almost every page has something that came from the Hubble. In a way, it's still great, it's still working, and eventually it'll get tired, but it's still working beautifully. So then we said, okay, what do we do now? Well, we launched it was out of focus. And so the picture shows you astronauts working with a Hubble telescope in space. And then this is the picture we got of a nice, beautiful nearby galaxy. But darn if it wasn't out of focus. So astronauts went up, they put in the correcting optics, and look at what happened. Suddenly, the worst disaster that had happened to NASA astronomy ever was the greatest success story we'd ever had. So astronomers looked at that and they said, yeah, we love this telescope now. And so we've kept on going. So a little while later, they wrote a book and said, this is the next party having a committee meeting, wrote a book that said, this is what our new telescope should be. Please build us one that's even bigger than the Hubble and cooled down to a low temperature so we can pick up what Hubble cannot see, namely infrared light. So that's how we did that. And here's a remarkable story about our leadership at NASA. The guy in the middle there, Alan Dressler, led the committee that wrote this book that said, please build us a new telescope. He went to see the head of NASA, Dan Goldin, up there. They liked each other, they understood each other. And so Dan Goldin went to our astronomy meeting and he gave a plenary talk. He's talked to all of us and said, why are you asking for such a little telescope? He got a standing ovation. That's a pretty rare thing for a NASA administrator. So we knew we better build this telescope. And he knew from where he'd come from in industry that it wasn't impossible. So he worked for one of those companies that build spy satellites. So he knew. So now we have a list of things we'd like to understand about where did it all come from. So where did the first objects form after the Big Bang? Well, let's say we believe the Big Bang story. That should be renamed the expanded universe story. What happened then? How did the galaxies grow? Where did the black holes in the centers of those galaxies come from? What about the dark matter that we tell you exists? And the dark energy we found out about recently? How does this all work? And how about those planets out there? So please tell us as much more as you can. So here's an example. And if we could now turn down the lights. Do we have control of the lights? Yay, thank you. Oops, the other ones. We're getting there. So this picture is a picture called the Hubble Deep Field, or eventually the Ultra Deep Field. The team decided to point their telescope at a blank place in the sky where there's almost nothing to look at. And what they found was thousands and thousands of galaxies in this one little piece of sky. So as far as we can tell, this is like most pieces of sky. It's got thousands and thousands of galaxies. And little blobs, they're all separate galaxies. There's one star in there, this little one there on the right with red and green spikes sticking out. That's a real star. The rest are all millions of galaxies. There are galaxies out there with billions of their own little stars individually out there. So we looked at that and we said, this is a big surprise. So why is it a big surprise? Well, number one, there's a lot more galaxies than we thought there would be. Number two, we're not able to see far enough away to see the first ones growing. So astronomers thought when we built the Hubble, we'd see the first galaxies. But you can look at the picture and you can't see them. They're not there. So why are they not there? Number one, they're too faint and too far away. They're too small. And number two, they're probably glowing at infrared wavelengths that the Hubble cannot pick up. So that's because the expanding universe has stretched out the light that we get from them. Was visible light, now it's infrared. So please build yourself an infrared telescope to pick up what used to be visible and ultraviolet light. So the committee wrote the book. So number one. Then we got a huge surprise a few years later from the Hubble. This is trying to tell whether the universe is full of matter or not. So astronomers believed for about 50 years that surely the expansion must be slowing down because gravity will slow it down. So some astronomers looked to measure and they said, well, it ain't so. Oops. I thought I had my picture of the astronomers, but nope. This is now a picture of what astronomers believe happened afterwards. So this is a simulation made in a supercomputer of the growth of galaxies. So if you believe my story that gravity did it, then we should be able to simulate the whole thing in a computer. Now that we've got supercomputers and supercomputers, we can do this. So what the computer folks have done for us is they've taken a box of universe, a hypothetical imaginary universe, and they set it going in a computer, and they make it rotate in front of our eyes so we can see its three-dimensional shape. And what happened was right away, as soon as things got started, galaxies were growing. And then here, at the age of a few billion years, the universe is starting to have explosions. This is because stars blow up occasionally, and also black holes form, and stuff falls in, and huge amounts of energy come out. So that would be a pretty dangerous place to be if you wanted to be alive. So the solar system did not yet exist at this point in the history. But you also notice that the structure becomes sort of stringy. The galaxies are strung along in threads and strings through space. There are huge spaces in between them with nothing, which we call cosmic voids. So now this beautiful movie is showing something you could never observe directly. You cannot see it with your own eyes. You have to use the computer to help your imagination. So here the universe is slowing down with its explosions. Just 9 billion years, that's when the solar system turns up. So we've only been here a pretty short time. Even our solar system's only been here a pretty short time. So anyway, I think this is one of the most beautiful movies you could imagine. Maybe you have to be an astronomer to really like it, but this is probably sort of like our history. So is it true? I can't tell you yet, but we're working on that. So that's another team project, by the way. There's some of the names of the people that it took to build that, and not even counting the thousands and thousands of engineers it took to build a computer. So we make progress as humanity together. So this is a picture of a galaxy sort of like ours, fairly nearby, illustrating several things. One is the giant spiral structure, which is sort of understood, sort of. And there's another little galaxy up in the upper right corner, and they are headed towards each other. So in a few 100 million years, there's going to be a giant merger. And they're both going to be completely re-scrambled and reorganized. In the lower right picture is a picture as seen, the same thing as seen by Lord Rosse, who was an Irish astronomer in 1845. And he had a telescope with a metallic mirror about this big. And he could see this structure. You can see he did a pretty good job of sketching it. So not bad for sitting on well, he was a rich guy. He had a castle in Ireland. But anyway, he had the time and the resources to build a little telescope. what we think of as little now, but it was huge. So here's another part of our story. This is a star that blew up on AD 1054 on July the 4th. So how do you know that? Well, everybody in the world could see it because it was so bright you could see it in the daytime. So astronomers wrote it down. We still have Chinese records, and you know what they meant. So this is a star that blew up, and this is a picture of it taken by Hubble. And now we call it the Crab Nebula because of how it looked to the first people with telescopes. But this is debris coming out. This is how the chemical elements of life got produced and released into space. So stars like the sun don't do this, but stars a bit bigger, they actually burn out fast and they blow up. So that's what this one is. And there's debris inside. It's a little neutron star. It's about 10 miles across. Spins around 33 times a second. But also pretty amazing. So we wouldn't be here without explosions like that. So I talked about the various catastrophic events that have happened in our history. This is similar to something that happened for us. So when you think about recycling, think about the atoms that you're looking at. When you look in the mirror in the morning, you are looking at atoms that came from something like that. So not only did your atoms have a big, long trip, of course, you also know you're breathing dinosaur breath, and your bones are dinosaur bones, and your water is dinosaur piss, and so forth. So it's good to be recycled. We're here and they're not. So now how are we going to learn more? Well, let's go build us a big telescope. This is the James Webb Space Telescope. I showed you the picture before, and this is a big word chart telling you who's working on it. So the team includes the 3 space agencies. Goddard Space Flight Center in Maryland, where I work, is leading the NASA part of the effort. We have companies all over the country working on different pieces of it. The big company is Northrop Grumman, a very large and famous aerospace company. And we have instruments coming from Canada and Europe. And the big rocket that we're going into space on is being purchased by Europe. So it's a lot like the American ones, but it's European. So when it comes time to go into space, we'll have to go to their launch site, and I'll show you that. So there it is in space. We'll show you a little bit more about how it works. For the amateur astronomers, this is a picture of how you focus the light. Light comes in from the right. It bounces off that big, more or less parabolic mirror, bounces off a small convex mirror, and goes through the hole in the middle into the instrument package behind. So we had to learn how to make this ultralight mirror. It's made out of 18 hexagons, and they're light enough you'd be able to pick up each one even though it's this big. So it's extremely, extremely good. And it was a huge project to get. Cost us a fortune, takes many years, and we're probably the only ones that need one. But anyway, we learned how to do it. We have a package of instruments. If you're an astronomer, you need to know this because you're going to write proposals for how to use them. Which objects in the sky do you want to point at? Well, we'll skip over the details. All I'll say is it covers the whole range of the spectrum from the red light that you can see today with a red laser all the way out to 28 microns wavelength, which is something a rattlesnake can pick up, but you can't. So we said, well, we should make this very powerful, and I will show you a little bit later about how powerful. But I just want to tell you some of the engineering that we have to do. First, we put the telescope together. There it is at Goddard Space Flight Center in its big clean room. Then we put it in a plastic bag and shook it to see if it would survive launch. Then we put it in its giant mailbox. We shipped it around the Capitol Beltway at night, drove the truck into this gigantic C-5 aircraft, flew it to Johnson Space Center in Houston, drove the truck out again, put the telescope in a big vacuum tank there, and tested it as it will be in space. Cooled it down to low temperature, made it focus, did all its tricks, and so we were very happy with it. Put it back in the mailbox, sent it to California, and is now in California about to merge itself with the rest of the observatory, which is being prepared for it. We will unfold it in California, make sure it folds and unfolds, put it back in a different mailbox, send it through the Panama Canal on its way to the launch site in French Guiana. That's where the rockets go up for the European Space Agency. And they'll push the button, it'll go into space, and after about a month, it'll be out in space, ready, well, not quite ready, but in space. So that's its trajectory. A little bit of the beauty of it. This is the mirror rotating around in our clean room at Goddard. Here's a picture of the robot putting the mirror together. This is a little bit, a very compressed version of what it takes to test the telescope. There it is in its plastic tent, being shaken. And we're rotating it around, putting it into the mailbox. Actually pushing it. Here it's going in. This is the door of the big vacuum tank in Texas. The truck bringing it. Going around the highway. The moon was up. There was a person whose job was to make sure it didn't hit, didn't touch. There's about an inch clearance between the mailbox and the airplane. Here it is coming back out again. Have to move some traffic lights to get under them. Who'd have thought you'd have to do all these things so an astronomer could have a telescope? But you do. So that's part of it. That's part of our story. And it's a heroic story for engineers. So I know I met a lot of physics students here who are going to be engineers, and I'm so proud that you're going to try this. So this is the vacuum tank in Texas where we tested it. By the way, this was built originally for the Apollo astronauts. They had to practice going down the ladder of their capsule and getting down onto the surface of the moon. So we put them in a vacuum tank, and we helped hoist them so they felt like they were in 1/6 of gravity, so they'd feel everything like it would be in real thing. And it worked. They were able to get down the ladder of their space capsule without tripping. And so that was important. Anyway, we had to change it. We had to make it cold, and that worked. We're very pleased with it. So there it is, temperature outside in Houston, 70 degrees, inside very, very cold. Little time-lapse movie of taking the telescope out again. We built a very short railroad. There it is, big, beautiful hexagon. Then we took it out to California, and it's going to meet up with this part. So this is another astonishing engineering feat. I just am so astonished at what it takes to do. There are dozens of people in this clean room doing things for, this is about a year's worth of work I'm showing you here. So this is the part of the spacecraft that has the rocket engines and the electronics in it. Now we're putting on the sunshade. The sunshade is the giant umbrella that's going to unfold in outer space to keep the telescope cold. And it is enormous. This thing that you see here is as long as a tennis court. Nevertheless, it will be folded up and will fit inside the top of the rocket. So when you see this, you can begin to understand why it was taking us a long time to do this work. By the way, you don't have to have a college education to be a technician in there doing this work, but you do have to be very good at it. Because this is a very tricky, difficult, hazardous in a way. Do not drop that wrench. Of course, we don't let them and everything's tied on a tether, so it cannot get away because we all make mistakes. Here we're lifting it up, preparing to fold it up. In this shape, it's all accordion pleated. It's all been folded up. So when people say we're going to go to Mars, you say, well, are you going to do it like this? It's nothing's easy about going into space. And the company that is building this for us said when we hired them, this is definitely not the most complicated thing they've done either. So of course that means they're working for the DoD. And they can't tell you anything more. Which means they're working for you. You just didn't know about it. So now we're practicing folding and unfolding. And we have to somehow manage to act as though this thing is like it would be in space, as near as possible. So when you say, well, how do you know it's going to work? Well, you test it, you practice. And you watch very carefully while you do everything. This thing all has to happen automatically by itself in outer space. We don't get to touch it. So rehearsal, rehearsal, rehearsal. So we should be proud of what they've done. We've still got a lot of it more to do. So where are we going to send it? We're sending it out 1 million miles away from Earth. This is a diagram of the Lagrange points in the orbits. So Sun, Earth, Moon, and then another 1 million miles farther out is the place we're putting it. This is our scary movie. Some of you saw the movie about landing the probe on Mars a few years ago, 7 Minutes of Terror, they called it. We have 2 weeks of holding our breath. But actually, we have something that they didn't have. We can stop and say, well, wait a minute, I think it's not working right, we have to do this. The lander on Mars had to do everything without our help at all, because we couldn't talk to it. So here it's unfolding itself in outer space, unfolding itself some more. And you say, well, that's awfully complicated. Are you sure you need to have it like that? And the answer seems to be there's no other way to get the discoveries that we're after. So you can call this the origami telescope. We actually made a tabulation at one point of 50 different ways to fold up the mirror. So can you make a self-driving car? Well, of course. If you can do that, you can do that. But it will take a while. So there it is in outer space. This is a view, of course, that you will never have. No one could ever have, because the computer is able to put light on the surfaces, and the telescope was going to be in the dark. Sort of the point. So what are we going to be able to do? We'll be able to look at bright things and faint things. If you were a bumblebee hovering out there at the distance of the moon, we'd be able to find you. Both from the sunlight you would reflect and from the heat you would emit. So that's how powerful this observatory is. And so it's because it's big and it's cold and it's got the world's best infrared detectors. We also want to look at bright things that are so bright you can barely keep up with them. And so we can look at Mars, even with this amazing thing. So we can look at all the objects in the solar system from Mars on outwards. So this is one of the things we're going to look at. This is called the Eagle Nebula, one of our prettiest pictures from NASA. A lot of people have this up to just because it's beautiful. This is a place where stars have just been born. They are being born inside this glowing cloud of gas and dust. And astronomers like me look at that and say, well, what's happening inside? I'd really like to see inside. So what do? You use infrared light. Infrared will see through things. So this is the infrared picture of the same place. Very different. So when you go down to the airport and you walk through the millimeter wave scanner and they look through your clothes, it's the same principle. Infrared light is longer wavelengths visible. It'll go around objects. And so the same thing. So we want to go around the dust grains and see inside and see stars being born. So we're going to do that. And the longer the wavelength, the better you can see in. We're going to look at places like this. Europa is a moon of Jupiter. It was discovered by Galileo himself. And the picture here was taken by a mission that we sent, and we called it Galileo. And what did the picture show? Europa is a little moon. It's a few thousand miles across, and it has an ocean covered over with ice. And it is kept warm inside by the tides that it gets. And it has geysers, water spritzers that are coming out. And people say, well, golly, isn't that a lot like Earth? Wouldn't you like to go find out if it's alive? So first thing is, can we please fly through the geysers and find out what's in the water that's spritzing out? And the next thing after that, can we go land over there and drill in and see what's in the stuff that's coming up? So this is clearly a good hint for where there might be life elsewhere in the solar system. Mars is not the only place that could be alive. Another place, well, let's go look for planets around other stars. So this happens a lot. If you point your telescope at enough stars, this will happen sometime. So we have built a telescope called the Kepler. We watched 150,000 stars for quite a few years, and we have a catalog of thousands of stars with planets that just happen to go in front of the star. So they blink, and you can tell how far away they are from the star, how warm they must be, how big they are from all of this pattern. So if you're lucky, you'll find something that's a little bit like Earth, and so far we only have a few that might be a little bit like Earth, so we got to look some more. So we have, and I got another picture coming. This is an illustration of one that was found using a telescope on the ground at first. They found a little star that's about the size of Jupiter, and it has 7 planets, of which 3 are about the right size and the right temperature to be like Earth. Wouldn't that be cool to know about? So, of course, we're going to go look there. Are they like, well, the oddest has given them all those planets colors. We have no clue what color they really are. But we'll come back later, and we may be able to tell you something about it, because number one, some of the planet's atmosphere may absorb some of the starlight on its way to the telescope. So we can analyze that part and say, what is the chemistry of the planet atmosphere way out there? And we'll be looking for water and methane and carbon dioxide and oxygen. So Webb telescope probably cannot tell you that it's alive because we didn't design it for that, but this is a step in the right direction. Okay, what do we got next? Okay, so people want to know, well, are we alone? So my opinion, probably not. But I think the neighbors are pretty far away. So how would you know? Well, first you want to know, well, how common are planets? Now we know most stars have planets. And a lot of them, maybe 1 in 5, has a planet the right size and temperature to be like Earth. But that's not all it takes. So Earth is very different from the others, even in our solar system. It's the right temperature. We have an ocean on the surface, and we have continents. We have just enough water to have both. It's not just rocks, not just ocean. So we're walking around because we have that lovely balance. We have a giant moon, which is probably important. We're the only planet that has a giant moon like that. We have a big magnetic field, which protects us from the sun. Maybe it's necessary that we have an atmosphere, because Mars does not have a magnetic field, and it doesn't have much atmosphere either. So a lot of special things. And the last one where I wrote here about the plate tectonics, we know the continents move around. It's quite possible that that's where life originated. If you want to know more about that, look, there's a lovely book called The Vital Question, where a British biologist has written up, where could life have formed? So there are places in the bottom of the ocean where warm water is bubbling up out of the ground, and it forms these gigantic, elaborate chimneys. And if you were ever going to design a chemical reactor that would try every possibility, you would build one of those. So nature has built them. So maybe that's where our first life forms might have occurred on Earth. So you would like to know, are there any of those on another planet? Well, how would you know? I don't know if you'd ever would know. But anyway, this is a way to hunt. So what are we going to do next? Well, we need bigger telescopes, of course. I'm an astronomer. I want a bigger telescope. So we're going to have our giant science party in another couple of years and argue about what's the next biggest telescope that we want to build after these. So that one might be chosen, maybe not. It's the one I drew there, that we drew, is actually really hard and really expensive, and we probably can't do it just now. But that doesn't mean we don't want it. We do want it. So we'll get there sometime. Not right away, but sometime. So we could also talk about, well, how far can humans go into space? Well, not as far as we'd like, because, well, it's easier to send a robot, mostly. Robots have been to all the planets, and a lot of dwarf planets, and comets and asteroids. We're really proud of that. The computers that run them are getting better and better. They can beat you at any board game, practically. They can play chess, they can play bridge, they can play poker. But an interesting challenge is that we are not any more tough. We're not any space, not any better at going into space than we were 100,000 years ago. So we need pretty special engineering to go. In the very long term, I think robots can go anywhere they want. But if you're a robot and you're an intelligent robot, you might say, well, I would like to go over there to Alpha Centauri and see what the planets are. And you could also say, jeepers, I would be lonely on that trip, because it's like hundreds of thousands of years to get there. So even a robot could get bored and could say, well, where are my friends going to be when I get there? So we don't know whether we're going there. Unfortunately, all the things that I read about in science fiction stories, they're mostly not going to happen, as far as we can tell. So Einstein was probably right. Stephen Hawking was probably right. We're not going there anytime soon. But anyway, they will have their chance sometime. So let's stop here, and we'll have some time for discussion. And thank you very much for coming. We are planning to have questions and answers, and there will be people with microphones.
Yes. So we have two students who will be running the mics. We have Duck and Anna. Duck is on this side, Anna is on that side. If you have a question, please raise your hand. They will come to you, pass the mic. As soon as you've asked your question, they'll raise their hand again, and please pass the mic back to them so that we can get as many questions answered as possible. So do we have any questions?
Launch date for the new telescope?
Well, we have one. We're planning on launching in spring of 2019. But right now we're thinking about that again. So we have a committee meeting to say, is this right? And I got a pretty good suspicion that we can't do it that soon. So ask again in a few weeks. We'll have the right answer.
Was there a question in the back? Yes.
I'm sure there are lots more questions. Oh, there's a microphone. Somebody will run you a microphone.
Yes, there was a question in the back. Anna will get to him, and then...
It may be a silly question, but I was just curious, why 5 layers spaced out like that to give it the solar shading?
5 layers, it seems to be enough.
And spacing.
Yeah, so we need 5 layers of the sunshade to keep the telescope cold. And 4 isn't enough. 4 might be enough if they were perfect. We need to have a little extra space. So the first layer stops the sunshine, and then the heat goes out sideways. So the spacing between them is to give place for the heat to get away out the sides. And by the way, they get punctured by meteorites out there. There's dirt in space, makes holes through everything. So 5 layers is to make sure that it's enough.
Hi. What worries you most about humanity? Do you think we get to 80 billion like you put up there?
Oh, good question. Well, I think we're all very intelligent individually, but our collective behavior doesn't always match our individual intelligence. So we can go completely crazy as a group. We can, as they say, nothing's so powerful as a bad idea whose time has come. So I don't know what we're going to do. We're also the only species that's ever known what we were doing to the degree that we know. So we can tell if we're messing up or not. And so what I can't tell is, are we going to do something about it? I think we will, because you can be crazy for a long time, but your kids will notice. And they'll take care of it even if we won't. So I think I'm actually very optimistic that the long term is warm and rosy for us. But so I think we'll be fine long term. But but things will change.
Okay, we have a question on this side and then a question over here.
Do you have a particular priority list as far as space exploration goes? Like, are robotic missions more important than, say, another manned mission to the moon?
Oh, good question. Well, there's two parts of that question. One is what's going to do the most for science, and the other is what do people really want to do? So for science, we need the robots all the time. They can carry the instrumentation that we can't do ourselves. We've got a rover up there on Mars that's got chemistry labs. I'll tell you everything about it. We're going to send another one with even better instruments. Is Mars alive? Well, you got to send instruments, and maybe even bring home some rocks. If you ask, do we need to do human exploration? Well, what's the point? There are lots of points. Well, we went to the moon to make a big point. We wanted the Soviet Union and the entire planet to know that we were bigger than they were, and so don't mess with us. So that worked. But that only works for a while, as you can tell. So now we have the possibility that individual human beings could have enough money to go by themselves. So Elon Musk could do it if he feels like it. He could go explore Mars, and he said he would. So I think that probably means he will. So we'll see. So we might need to say, hey, Elon, wait up a minute. We want to find out if Mars is alive before you cover it with E. coli. So we do have a few things we ought to talk about. We do have, by the way, an international treaty that says we will not contaminate places that could be alive. We have to sterilize all our spacecraft very completely, so we don't send Earth life there before we find about Mars life or life on Titan or something. So that's a good thing to have. So if Elon wants to go, we got to have a conversation, right?
Anna, I think there's a question here on the third row. This gentleman here, and I see you too.
The Hubble, when there was a problem, an astronaut or several astronauts solved that. You won't have that on this. Is that what you're expecting to do it with computer data or robots?
Your question is, what happens if it doesn't work perfectly, basically? And of course, we anticipated that. That was our very first question to ourselves. Well, what are you going to do to make sure that it still is okay if you can't go fix it? So number one, you have two of everything if you possibly can. So every one of those motors, there's two ways to make it turn. Every really important piece of electronics, there's two of those. And so we have ways to do that just so this stuff goes wrong. You have to test it and rehearse it a lot. So my history shows that if you do not test something, it will not work. So we will test everything. And so, but then there's a limit to what you can test. So then we have to say, here's the long list of things that we know we need to test, but you can't not possibly test. So let's really think about those very carefully. So with the Hubble, I think we know what this mistake was that they made, and so we're not going to do that one. Let me sort of summarize what that big mistake was, because it happens to a lot of people in a lot of different ways. They said, here's the mirror that we made, and we know that it's good because we tested it this way. It turned out the yardstick they used to measure it with was the same yardstick they used to build it with. So they didn't anticipate the possibility the yardstick was wrong. So if you really want to know if something's right, you've got to have two different sets of people with two different sets of equipment to do the same measurement. So if they'd really done that, if we'd known how important it was, of course, we would have found out. So right now, you can go see the good mirror that's over in the Air and Space Museum in Washington, because there was another company that had built another good one, and we could have used that one, but we just didn't know. So that's the general answer. Measure twice, cut once, like the carpenter said. Or measure 3 or 4 times, even. Okay.
There's a question right here. Yeah, raise your hand high.
Okay. There we go. Somebody had a question? No. Very good. Yep.
Professor, do you think life already had a chance in the universe when the cosmic microwave background temperature was still a balmy 50 degrees Celsius versus close to 0 right now?
So you're asking, could life have occurred when the universe was younger?
That's right.
I imagine so. I don't think the cosmic microwave radiation has a lot to do with it. But what what we're curious about is, were there any stars with planets with the right chemistry at that time? And so there could have been, but there wouldn't have been very many. And it could be that maybe there were a few, but we wouldn't know. We would probably never know that answer to your question. Some questions are beyond us, and we're probably always beyond us.
Mike's coming from this side.
What is the composition of the hexagonal plates on the James Webb, and why did you choose those materials over others?
Okay. Why is it what we did? Well, the short version, the social version is we tried everything, and that was the one that worked. We had a competition. We do everything by engineering competitions. So company X, Y, and Z, they all say, I can build you one of those. And we say, okay, here's some money, you show us that you can do it. And so we had 12 contracts to different companies that could you prove that you can do this? One of them worked. So what was the one that worked? It was, we'll build it out of beryllium, and we'll coat the beryllium with gold. So you see gold, but the material really is beryllium. So why beryllium? It's really light and really stiff. And it's a pain in the neck to work with because the powder can kill you. So the original machining is done inside a sealed, hermetically sealed box with water jets. Every single particle of beryllium is captured, sent back to the factory to be melted down again. So then it's really hard to polish it. It's really hard to treat it properly, but we had to learn how because it was the only thing we could do. So next time maybe it'll be a different answer, but this time that's what it was. Gold, by the way, because it's the best reflector for infrared light.
We have one question here in the back.
So if I remember correctly, the Hubble telescope wasn't able to see the first forming galaxies. Is that the hope that we can have with this new one, or what are the new parameters?
Yes, that was actually one of the main original objectives of this new telescope, is to see the first galaxies growing. So, of course, you don't exactly know what you're looking for. So your objective is to see the farthest and faintest things you can imagine and try to figure out what they are. And then there's always a chance that you'll say, I'm sorry, I still didn't see the first one. But we'll get as far as we can imagine getting. So the hope is that we'll see some little glowing infrared dot out there and we say, that's exactly what we thought it would be. And then you say, now I'm happy. Or you could say another hope would be, I found something nobody thought was going to be there, and now you're happy. So I'm hoping for that one, to tell you the truth, some surprise, something that we didn't all think was going to be there.
I think there's two questions right here.
Okay, so this is supposed to be going really far out, I'm assuming even probably further than the Hubble. How durable is it going to be? I mean, if something really big hits it, is there going to be major damage to it, or is it going to outlast that?
Oh, how is Hubble doing?
Well, how durable is the newest telescope?
Oh, the telescopes, they're pretty darn durable. There are two things that make things wear out in space, or a few. One is electronic parts just fail when they get old. And so we try to deal with that by having two of everything. Sometimes they fail because you just can't help it. The cosmic rays damage them. Sometimes it's just a random event. A meteor hits something. That has happened. So we had to design our observatory so when the little meteorites hit, they won't puncture any cables. We know they're going to make little holes in the mirror, but we don't care. But hole in the cable, we would care. So we could run out of fuel. We will run out of fuel. That's the planned end of life for the Webb telescope, is we run out of fuel. So we need fuel to keep it pointed in the right place, and we need also fuel to keep in the right orbit. So we'll use up the fuel, and after 10 or something years, we'll be out of business.
This way.
So you mentioned when you take spacecraft to Mars, you have to go through a sterilization process. What's that like?
Oh, how do you sterilize a thing to Mars? Well, first you try to wipe it down with alcohol and solvents and the things that, so get all the major dirt off that you can see. And then you mostly toast it. Most things that you can imagine do not like heat. But of course, neither does the electronic box. So at a certain point, you say, well, I can't get it any hotter than this or my electronics will fail. So then you stop. So you've done the best you can imagine doing and hope for the best. So it's possible that when we do get to Mars, we'll find that there was something that we took there. But I think probably we won't find it. So it's hard to imagine, actually, that any of our Earth-like bugs would like Mars very much. But you never know. If they can grow potatoes, as the Martian movie showed that you could, then maybe other things too.
I'm a programmer. I'm curious about the data that's going to come back from the satellite. Will it be in open data formats, or how will we get it?
Okay, well, it'll be like we do for the Hubble Space Telescope. Some of the data will become public immediately, and you can just download it from the servers over at the Space Telescope Science Institute. Others, some of the data will be kept by the principal investigators for their personal use with their team for up to a year. Then it becomes all public. So it'll all eventually become public. In fact, most of the research papers nowadays are based on the archives. So you can have it, and you can make pretty pictures of it, and you can figure out what it means. So thank you for trying it. And we'll have copies around the world, so everybody will have at it. And it'll be beautiful.
I think I saw another question here in the back.
You kind of touched on this earlier, but you said that logically the universe's expansion would be slowing down, but in reality it's speeding up. What's the reason for that acceleration?
Well, in a way, it's a reason. We call it the dark energy. But actually, all it is an observation. It's speeding up. And then we said, we'll call the reason dark energy, which means we actually do not have a clue. Now, Einstein did allow for this in his equations, but he didn't expect it. At first he did expect it, then he said, no, that's wrong. And then finally we had to put it back in because of the observations. But hardly anybody expected it. When it was discovered, the young people that first found it had to do it over and over to make sure they were right. You get some surprises. They got their Nobel Prize, by the way, for discovering this acceleration.
Yeah. So I think we've had a lot of questions, and I think they're great. I think we have time for maybe one more question, and then we want to present Dr. Mather with a special award, a gift. So.
Can you talk about the micro shutters that this telescope uses and how those get images for the telescope?
Oh my golly, I didn't even mention them, so you must know a lot about our telescope. So micro shutters, well, we said we want to get the spectrum, the rainbow of each of those interesting galaxies out there, and it's so hard to do, we want to get 100 of them at a time. So how are you going to do that? Well, you have to let in the light from 100 galaxies and keep out all the light from all the others. So we said we're going to make a little square, and we're going to cover it with little tiny shutters that can open or close by command from the ground. And so now we've got it. We've got 250,000 little tiny shutters that you can open. So when you line it up, you say, I'm going to open the shutters for the galaxies I'm interested in, and I'll get the spectrum from each one all at once. So that's a huge engineering challenge because those shutters are tiny, and you have to make them open up remotely. But we did it. So people at NASA Goddard invented that process. So we're just proud of what we do. Yeah, thanks.
Thank you guys for your questions. Let's just give Dr. Mather another round of applause, please.
Well, thank you, and thank you on behalf of the engineering teams that are doing the miracles that I showed you.
So the students here would like to present you with a gift of things that they've made for you.
Okay.
Let them tell us about what you
so we'd like to show our appreciation for the time that you've taken to spend with us. And on behalf of all of us, and particularly Rhodes Engineering, this is an engraving of the cosmic microwave background.
Oh, and it's got the texture. You can actually feel the bumps. Yeah. This is the first time I've ever felt the bumps in the cosmic microwaves.
Yeah, right?
Thank you. That is brilliant. Thank you so much.
And also, this is the 3D model of the James Webb telescope. And I made it small so that you can carry it around, not like the other one.
Oh, thank you. It is also brilliant, and it is indeed very small. Thank you so much.
Then we have one last gift that we would like to give you to kind of help commemorate your time here as the Peyton Nalle Rhodes speaker. We have a picture frame here, but in here it says it's 2018 Peyton Nalle Rhodes Lecture Series. And thank you from Rhodes College students and faculty, and then it's just a picture with you talking to some of our students this morning at the breakfast.
All right. Thank you. Yep. That was a good conversation. Thank you.